the inverse of a matrix. So with a square matrix A, if you wanted to write the inverse, we use the same inverse notation, a to the minus 1. And the product of a matrix and its inverse is the identity matrix. Which is, if you have a 2 by 2, it's ones along the diagonal. Okay? Now, if you have a 2 by 2 matrix, here is the simple way to find the inverse. I don't know how simple it looks. Easy. So what happens is you do 1 divided by AD over minus BC, which happens to be your determinant. So that's why we were doing determinants last class. Then you switch the A and the D values and make your other values negative. And that's why you can't have the determinant be 0, because then you'd be dividing by 0 here, which we have in our notes right here, I believe. No, not yet. Right there. Okay? But if your determinant is 0, then you can't have an inverse because you'd be dividing by 0. So in order to find an inverse, you have to first find your determinant. So our determinant of this matrix is equal to 1. And therefore, the inverse is 1 over 1. You go to your matrix, you switch these two values and make these two values negative, and we have our inverse. And if we look now, what would happen if you would multiply 3, -1, -5, and 2 multiplied by our original matrix, 2, 1, 5, and 3. Okay, matrix multiplication. And I'll color code these. We'll start with green. If I do row 1 times column 1, you will get 6 minus 5, which is 1. If I do row 1 times column 2, I will get 3 minus 3, which is 0. Row 2 times column 1, -10 and 10 is 0. And finally, row 2 times column 2, you get -5 plus 6, which is 1.
So you know if you did your inverse right then?
Yeah, I guess you could check by multiplying them, but it is a little bit tedious.
It is.
Okay? In our second one, if we wanted to find our determinant, this is 3. This is 0. 3 minus 0 is 3. So our inverse, 1 over 3, switch these ones, make these ones negative. And you could either write it like that. If you happen to check it on your calculator will multiply that 1/3 inside and come up with that value.
But you don't care which way we play it?
I like the 1/3 out in front, because then if you're doing any kind of multiplication afterwards, for example, if that's my inverse, I could choose my inverse to be with the 1/3 out in front or like this. But if I wanted to check if my inverse was correct, my original matrix there was -3, 2, 0, 1. It's going to be a lot easier to multiply these matrices with whole numbers than it would be to have that fraction in there. So I'm going to multiply first. -1 times 3, this will be 3, 0, 0, 3. And then multiply by that 1/3, and sure enough, we get our identity matrix. But it's easier to multiply using those whole numbers than it would be to use your fractions all the way through. All right, and here's the note that we talked about already. If the determinant is 0, okay, and a reminder of this definition. If the determinant is 0, we can't have the inverse, and now we see why. Because you can't have that 1 over 0 as the process of finding your inverse.
When a singular matrix is used in the real world, matrices,
When are singular matrices used in the real world? Well,
or used as a way
I don't know if I can, off the top of my head, think of, oh, this is a place that you always end up with a singular matrix. But if you're solving a system of equations, there's some systems of equations that have no solution,
all right, that makes sense.
right? Two parallel lines that never
That would be
intersect.
the category.
And it just will tell us from that that there is no solution.
That makes sense.
So we can find inverses with our calculator, just like we can find almost anything with our calculator, with matrices. Put in a matrix in A, then just push your inverse button with that matrix and it will calculate it. And for all of our 3 by 3 matrices, we will be finding them with our calculator. So I'd like you to type that into your calculator. I'll show you it by hand as well. How did you do? Did you find? That is your answer. Okay? And then if you wanted to factor out the 1/6, what I suggest doing is taking your answer, multiplying it by 6, or divide by 1/6, the same thing. Okay? So there's our inverse. The question is, how would you find that by hand? And I don't have notes for it here, but I found it 2 different ways on the internet. I'll show you both of them. Okay, method number 1. We get to learn a new fun word, creating the adjugate matrix to find the inverse matrix. Okay, first of all, you find the determinant. We find the determinant of this matrix to be 1. That allows you to say that the inverse does exist. So we check that first. Okay. You transpose your original matrix. You don't have to remember any of this. You can look it up later. But this is just showing you how not so simple this could be. Okay. You find all of the little mini determinants of your transposed matrix. There's only 9 of them. This shouldn't take you too long. Okay. So each of the little mini matrices that are in there. Okay. You take all of those numbers, and that makes your adjugate matrix. And once you have them, you multiply by this plus minus, plus minus, plus minus, plus minus to change some to positive, some to negative. Okay?
All it is just a series of pluses and minuses. If the previous one was plus, then minus. Otherwise, minus. Sorry.
And then your inverse is 1 over the determinant times by that adjugate matrix. Method 1. Method 2, which I prefer.
Just pull out your calculator.
No. And we're going to use this technique as something that we learn later. Okay, so this technique will, and this is probably the reason I like this better, is you set up the matrix you started with, and over here, you put your identity matrix. And what you want to do is you want to do things to your first matrix to turn it into the identity matrix. But while you do those things, you do that to the identity matrix on the other side as well. So for example, okay? For example, if I want to change row 1 here, I can change row 1 by taking row 1 and adding row 2 to it. So row 1 plus row 2, can you see that row 1 would become a 5, and then this would become a 0? And the reason that'll be handy is if I now divide row 1 by 5, I get a 1 in the top left-hand corner, which is closer to getting this first half to be 1, 1, 1 on my diagonal. Okay? I can now make this a 0. Okay, I should scroll down here for you. Can you see in row 2, I think that's what they're going to do next. They can make row 2, they just go dot, 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 keep on working. But what I would do next is I would make this row 2 a 0. And then I could add row 3 to row 2 to make that a 1. And then I could eventually make this one a 0 and continue until you get all 1s and 0s here, and whatever you're left with over there will be your inverse. But we're going to, for a 3 by 3, do trusty method number 3, which is plug it into your calculator, push a button, and voila! You get your answer. How do you know it's right?
We trust.
You could then take f inverse and multiply it by f. Did you bring me one? No? You didn't bring me one?
Oh yeah, I have one.
Okay. Whew. All right. Good.
Is that a tequila? It is.
I don't know if you want one of those.
So good, actually.
There's,
Good, but just off.
oh, I think I might like one.
We wanted to die earlier.
Okay. Application of inverses. We can now solve our system of 2 by 2 matrices in a new way. Okay, you already know how to solve this. Maybe you would use elimination technique. Take this one minus this one, what would you get? You would get negative y equals 9. Y equals 9? No, I subtracted. Oh yeah, y is equal to negative 9. There we go. Yeah, that's good.
I was scared for a moment.
No. And then if y is equal to negative 9, then what would x be?
It will be 1/2
Negative 5.
negative 5.
Negative 5. Because you could plug it in. This will be 9 subtracted. And so x is equal to negative 5. So we already know how to solve this. And we probably know how to solve it better than using inverses of matrices. But we're going to look at how inverses of matrices could be used to solve this as well.
When would it be better to use it?
It gets real neat.
Well, if you go to a 3 by 3 and have the use of your calculator, then it might be faster. But
Remember this stuff, Christian? I remember this is why we learned
So-
matrices. I don't remember.
I remember doing
this
you
math
just
class in
isolate
school.
y and
I have no idea how to
set
do
them
it.
equal to each other.
you could.
Was what, in the 8th grade?
Okay.
It was summer.
So what we do is we take our system of equations, we take the coefficients and make a coefficients matrix. We take our variables and make our variables matrix. And we take our answers and make that a constants matrix. And with matrix multiplication, do you see how this would work? If in green I do this by this, what will I get? I will get 4x minus 2y. That's matrix multiplication. Multiply them, add them. And if I would do this times this, I would get 4x minus y. And if the green ones were equal to minus 2, and the purple ones were equal to negative 11, that's my system of equations. So I've taken my system of equations and turned it into a matrix multiplication equation. I then say, if A is my coefficients matrix, X is my variables, and B is my answers matrix, I can then algebraically solve for X by multiplying by the inverse. And now this is where matrices, you know how matrix multiplication, it matters the order. A times B is not the same as B times A?
Yes.
If I want to get rid of this matrix A in front by multiplying by the inverse, if this inverse is in front here, I have to multiply in front there. It would not be okay to just do, you know how we go like this?
Yeah.
That would lose a mark, because that's not true. right? The order matters in matrix multiplication.
So like you're gonna give us a little gap between the equals and the B.
Well, no, you can do you can do this. That's okay. Oof, feels weird, right? Or you can just not write it there and take the extra moment to write it there.
Wow, you're
No.
asking too much, Ramsey. What? I'm not asking it. No, of Ramsey.
And so now this becomes identity matrix, which means you just get x on this side, and x is equal to A inverse B.
Because A inverse and A cancel each other.
That's right.
Right?
And so our matrix here, we have our matrix equation, which is 4, -2, 4, -1, and xy equals -2, -11. If we multiply by the inverse, well, the inverse multiplying will make this side go away. The inverse of this, again, this will be -4 minus a -8. 1 over 4. Switch these ones, -1, 4. Opposite signs here, 2, -4.
And then times that. That really messed me with the 11, like the on the top one.
It's not quite long enough. There we go.
It kind of looks like the Wi-Fi bars.
Oh yeah, I said, yeah.
Yeah,
Pretty weak signal.
Weak signal. 11.
No.
That's 111, which is stronger than an 11.
That's what they're going to teach numbers in the future. All right. 2 1s, 11.
All right.
5, I think, over 3 1s.
And now, if we multiply this out, I'm going to put the 1/4 still there. I'm going to multiply here. This is going to be 2 minus 22, -20. 8 minus 44, -36. Multiply that 1/4 through, which we already knew x was going to be -5 and y was going to be -9, but we get the same answer using matrix multiplication.
And you can use it with multivariable like x, y, z.
You could have 3-dimensional equations, but then you would, yes, but you'd still have to use your calculator to get an inverse. Okay? Now, this only works with square matrices, but if we take that and apply it to systems of equations, you can't solve a system of equations with 3 unknowns and 2 equations. You need 3 equations with 3 unknowns. You would need 4 equations with 4 unknowns. So it'll always create square matrices. And if you have 5 equations with 4 unknowns, one equation is redundant. You just don't use it, solve it with the other 4. You'd still have to check that your solution works with your 5th equation, because it might be the 5th equation ends up not making your system true. But if it does, then you will have solved it.
Oh yeah. Sorry. So you're multiplying the.
Off to the side to help see what I did, okay, is first of all I set up my matrix. So I'm going to call this A, this matrix X, this B. Okay? And so we can follow along with what I did. I kind of skipped a step here in that this step here is saying X is equal to A inverse B. Because the step I didn't want to write was A inverse times A times X is equal to A inverse times B. Adding this A inverse on both sides. Right? If I add an A inverse multiplied in front of one side and I add an A inverse multiplied in front of the other side, that keeps it true. And A inverse times A is just 1, or it's the identity matrix. And then identity matrix times any matrix is just that matrix.
A inverse A is also equal to A times A inverse A.
Yes. Because they're both the identity matrix. That's the only time that the opposite direction works. What's that? Yeah, what I would often do is just show this with maybe letters, and then write this out. That's where this is my x. My A inverse is this 1/4, and then there's my matrix B. The 1 over the determinant.
You do the A one, you get the determinant A.
What do you do while we
Because that's the formula.
That's the formula for the inverse.
So you would find,
Here is our setup.
alright,
AX equals B. Again, I'm showing what I'm doing with my letters here. So then I can set up what X is going to equal. There's my inverse. And then you get 1 and -1.
This one? Wait, which one is this one?
This is the first one.
I got one without it. Someone take this row. Oh, never mind.
You're good? Okay. Go up a little bit. This is the first one. Did you have the right inverse?
So then you get.
Yeah, but I don't think I got one flip. I didn't get one flip.
Okay.
well, then you double check like
So here, if I do
It's minus a -2.
3 minus a -2, will give you 5.
Yeah, X is 5, Y is
Because on the second one you got 15 minus 31 to -16 minus 4, -4.
That's right, yeah.
So I would, on this one, first of all, in order to get your coefficients matrix, you're going to need to do some work to rearrange this equation.
So it's 1 and negative. We just flip it. What's the answer?
Okay? And then, well, we'll put it up here soon. Then you can set up your matrices. That is the most beautiful -1 you've ever seen in my notes.
Is this the next one? Oh, I didn't even start that. Wait, that's the answer?
There's the answer.